Isn't 25 equal to 3 times 8 plus 1? It fits the form 3k plus 1. So give me another one, please. 16? In stereo, nice. 16 is equal to 3 times 5 plus 1. Fits the form. Okay. How about, I don't know, 169, right? That's a perfect square. That's 13 squared. So that's going to be, shit. 3 times, what do we have here? 56 plus 1. Okay, thanks. I was getting there. Guys, they all fit a perfect square form. Even something like 0, right? 0 is a perfect square.
3 times 0.
3 times 0 plus 0, right? So all of these perfect squares look like they fit this form. Okay? Now it's our job to be able to prove that statement. Okay? So does everybody see like why somebody might actually want to use the quotient remainder theorem in real life? Okay, it actually does hold some sort of value to people. Okay, not just to us, but like people that like to program stuff. Okay, so let's go ahead and prove this. Okay, and by the way, if d equals 3, somebody remind me, what are the different outcomes that could occur if d equals 3?
0 on 2.
We'd only have 3. Do you remember what they look like, sir? If not, that's okay.
3 times 0 and
3q plus 0, 3q plus 1, 3q plus 2. Perfect. Like it was up there, it was just coming out. Good. That's very nice. So guys, wouldn't we have 3 cases for this problem? Okay. Fortunately, I didn't let d be equal to 16, because that means there would be 16 cases. Okay, so let's start by saying, let's let, we can just say x, it doesn't matter, be an element of the integers. Okay. Where x is equal to dq plus r with d equal to 3, okay, and 0 less than or equal to r less than d, and we should also make sure that we define r and d to be integers as well. So basically, guys, all we're doing is we're just utilizing the quotient remainder theorem here, right, guys? That's all we did at the beginning of class. Okay. We can also say by the quotient remainder theorem, and I'm going to put this in brackets because we don't necessarily need to write this. Okay. So by quotient remainder theorem, okay, Mr. Williams, you're absolutely correct. There's 3 possible outcomes. X could be equal to 3k, 3k plus 1, 3k plus 2. Okay, and then since that's a comment, we don't have to define what k is. Okay. But I'm just saying this like just in case you have a problem like this at home, okay, for your homework, and that this might be helpful for you guys to remember how we define those. Okay, not saying you have to write it, okay, but it might be helpful for you guys to think about where this is coming from. Okay. So, everybody good with the definitions? That's pretty easy, right, guys? Okay, so we have case 1. Okay. Case 1, let's let x be equal to 3k, where k is an integer. Okay, so now we have to define k as an integer, because it's no longer in the comments field, if you would. Okay. Next thing we do is substitution, right guys? We define the variable, we use substitution. So by substitution, what are we substituting into?
Either of them, 3k or 3k plus 1.
Unfortunately not R. Good try. Because that's what we want to end up with.
Oh, and that is
Okay, we're going to substitute into x squared, right guys?
square, okay. Yeah.
Because aren't we trying to show that the square of some integer has the form 3k or 3k plus 1? Okay, so by substitution, x squared, since x is equal to 3k, is equal to 3k quantity squared. John.
I'm going back to the first thing real quick, where you define R and D as integers. Isn't it Q and R, not R and D?
Hold on a sec.
So I looked at
Yeah, it should be, you're right, because we've already defined D to be 3 constant, so yeah. Sorry about that, I'm just making sure, you're correct, John. Sorry. Tactical error on my part. Just take a half point off of my proof there. So now I'm down to 9.5 points. Oops. Or you just write in the teacher evaluation. Doesn't know the difference between a D and a Q. Sorry about that, guys, but good catch, thank you, sir. Okay. What seems like the most obvious thing to do at this point, guys? Yep, just expand it to 9k squared, good. Okay. And we'll write in the steps after we're done here. What are we trying to show that 9k squared is equal to?
3k,
Or,
3k plus 1.
right, one of the two forms, right? Doesn't it look like it's going to fit the form of 3k?
Yeah.
All right, so how do we make it look like 3k?
Take
Is that
square
right?
root.
factor out 3.
Yeah, we can just write it as 3 quantity, 3k squared, just by a common factor there, or just by computation if you would. And then guys, don't we know that 3k quantity squared, or quantity 3k squared is just like a p or something like that?
Yeah.
So that's going to be equal to 3p, where p is an integer. Okay, like I said, I'm going to write the steps in a second. Right? But does that make sense, guys? We need to show it fits one of these two forms. It doesn't matter which form it fits, it just has to fit one of those two. Okay? If I were to fill in the steps, multiplication, factoring, closure. And there we go. We're done with case 1. Okay? Yeah, me too. The bad news is that we still have to do case 2 and case 3. Okay? So case 2 is going to be basically the same thing, except this time we let x be equal to 3k plus 1. And again, what we're doing is we're just exhausting all the possible outcomes from the quotient remainder theorem. Okay? So we're basically utilizing some of the stuff we did on the first test with exhaustion, except we're doing it at a much higher level. Okay? So for case 2, yep, I can and I will. Is that good, John?
Yes.
Okay. Yeah. By the way, guys, if I'm going too fast, let me know. I'll slow down. So, case 2. I know I get all happy about this stuff and I start writing quickly. So this time, let's let x be equal to 3k plus 1. Okay. Oh, go ahead, Rob.
And where are we getting these substitutions?
These are coming from the quotient remainder theorem. So remember when we defined that the possible outcomes when d equals 3 is either 3k, 3k plus 1, or 3k
So
plus 2.
in 3 cases.
Correct, right.
And,
Go ahead.
and why do we use 3 as the...
Oh, because what I said was, prove that the square of any integer is 3k or 3k plus 1, and I just gave you the hint to do it. Okay.
Gotcha.
I'll try to give you guys hints where, like in real life, you just have to basically think to yourself, how can I get to that form, okay? But in math life, I'll give you the hint. We'll see. Okay, does that help out a little bit, Ryan?
Yeah.
Okay, good question. Okay, so we're going to let x be equal to 3k plus 1. We're going to substitute. So by substitution, we can say that x squared is going to be equal to quantity 3k plus 1 squared. Okay. Now, we don't want to use closure. Okay, you don't want to use 3k plus 1 as p, because then you just get p squared, right? You don't get 3p or something like that. So I often see students try to use closure incorrectly right here. While it will get you p squared, it won't get you the form of 3p or 3k plus 1 or something like that. Okay? All right, so what do you guys suggest we do at this point?
Expand.
Go ahead, James.
Multiply it out.
Yeah, we're just going to FOIL it out, right? Okay? So if you guys go ahead and use your FOIL, that's not going to be 9k squared plus 1, right guys? But remember, it's a binomial. And if you don't know what it equals to, you just go off to the side and do it. Okay? But correct me if I'm wrong, 9k squared plus 6k plus 1. Okay? Does that look good to everybody just by using the a plus 2ab, a squared plus 2ab plus b squared? And again, If you can't see that, okay, better be right, just do this off to the side. Okay, just do 3k plus 1, 3k plus 1, 9k squared plus 3k plus 3k plus 1, 9k squared plus 6k plus 1. Okay? So, I don't want to see anybody doing like the freshman's dream where you think you can just distribute the square through there. Alright, don't ever do that. Alright, if you ever did that in your life, hopefully your teacher yelled at you for doing that. Alright, so what do we do at this point, guys, now that we have this form? Yeah, GCF of 2, right, Donnie? In the first two, okay? So if you factor that out, or sorry, GCF of 3, done. Yeah, it would kind of hard to be factored out of 2 from that, because then we get some fractions. Not saying you couldn't, but you wouldn't. So 3k squared plus 2k plus 1, okay? Good. And then, guys, what does this equal?
3p.
3p plus 1, right, guys? And that's one of the two forms that we wanted to see, right? Remember, it's either 3k or 3k plus 1. So we could write this as 3p plus 1, where p is an integer. Okay?
We can also do 3p too, right?
No,
By closure, you can do 3p?
no, sir. Because if you factor out, let's
Oh,
say,
okay, I got you, 130 up there.
if you factor that out, that would be rational. It would no longer be integer closure,
Yeah,
okay?
got you.
So yeah, you can't use rationals and integers together. They don't play nicely.
Yeah.
Okay. All right, guys. So does that one work for everybody? Any questions so far? Okay. Last one, case 3. Oh, yes, there is. Yeah, because remember we said that there was case 3k, 3k plus 1, or 3k plus 2 by that quotient remainder theorem. Okay. So this one actually does have 3 cases. Sorry about that. The good news is you guys only have to do this once. I have to do this for the remainder of my career twice a semester, which is going to be another 30-some years if Social Security holds up. If not, well, yeah, I'm screwed. Oh well. That's why they make alcohol, to preserve my liver. That's what I keep telling myself. So we're going to let x equal 3k plus 2. We're going to substitute again. It's basically going to look like the previous one. Okay, so let's just bully it and get it done. Okay, so by substitution, x squared is going to be equal to 3k plus 2 squared. All right, and then correct me if I'm wrong, if I were to FOIL this out, 9k squared plus 12k plus 4. Not 12 plus 4, 12k. That might be helpful. Yeah. Oh, you suck. Yeah, I'm getting it. Thanks, technology. I forgot the K in there. Okay.
On case 2 and case 3, since they are unrelated each case, shouldn't you mention that k is a...
At the end of the oh, I see what you mean.
You should x equals 2k plus 2, where k is...
Yeah, I forgot to put that in there, didn't I? Thanks, Mr. Weber. So we should say in here that K is an integer, which is why I purposefully let all this space in here.
Right.
Right, exactly.
That
I definitely wouldn't forget anything.
subconscious forethought.
Subconscious, yeah. So thank you, sir. Appreciate that. You're absolutely, yeah. Every time we're in like a local stage, if you would, you want to define an integer. Okay, thank you, sir. All right. So at this point, guys, we can go ahead. We could factor a 3 out from the first two. Actually, no, we couldn't yet.
No, 9k squared
We have
plus
to write 4 as 3 plus
Plus
1,
one,
right, guys? Okay. Sneaky, sneaky. So this would be equal to
9k.
yeah, 9k squared plus 12k plus 3 plus 1.
Now you
Yeah, now we can factor out that 3. Now we can write this to 3p plus 1. Mercifully. Okay, so let me let you guys copy that down for a moment.
Why is it 3p plus 1 and not 3p plus 2, like the?
Oh, remember what we're trying to prove, Andre. We're trying to prove it's either 3k or 3k plus 1. That's the original. We substituted 3k plus 2, right?
Why did we substitute 3k plus 2?
Remember we said that D has to be equal to 3, right? And so it's one of those 3 cases that we started with.
Okay, so it's one of the cases where we're trying to prove the original.
Right, we're trying to prove all the way back up at the very, very beginning, okay? Right, because I do see that often, or not often, but enough, where somebody will try to prove the substituted part, okay? Just because you're substituting it doesn't mean you actually want to prove that substitution. You want to prove the original, okay? Great.
Would you actually be able to do that? It's like I can almost quite do it. but-
Right. You shouldn't be able to prove it's equal to 3k plus 2. And if you can, that means you could have found a counterexample at the beginning, and we just wasted 25 minutes of our lives. Okay? Not saying that some of you guys don't think we've already wasted 25 minutes, but we would have truly wasted 25 minutes. Okay. All right, is this good, guys? Any questions? We'll finish this out. Okay, so, very last line, we can say thus. X, remember we defined x to be equal to dq plus r. So x is either equal to, or thus by, sorry. So thus by case 1, 2, or 3, x is equal to, or x squared, correct. So x squared is equal to 3p, or x squared is equal to 3p plus 1.
Why not and?
No, you can't have and, right? Because that means that at the same time, x is equal to 20 and x is equal to 21, and that's impossible. You can't have a singular variable equal to 2 instantiated values simultaneously.
We say it that way.
Right,
That-
okay.
yeah.
Yeah, you have to be careful with that wording, okay? So, now if you put in by accident, I'd probably scratch it out and say never ever write that again, but